Hey, good. We have a lot of stuff to do, so we're going to do a Kinga. What are you doing here? Can you please be silent then, or go away? Go away would be preferable. Good. We're going to go over the homework. We're going to do it. Wait, hey guys, remember how we never finish? That's because we're screwing around, so let's not do that. Let's instead do the opposite of screwing around, which is very, very efficiently learn. And the first thing we're going to do is go over the homework, which was, I believe, 8 problems on the topic of calculus of parametric curves. How did it go? Good. Let us pick, say, 4 of them to do right now. I think I am just going to do it. 24. I say we should do 39. I say we should do, did I assign 34?
Yeah.
34. Is that maybe just good enough? Maybe one more. Maybe, did I assign 14? No, did I assign, what else did I assign? 189. Let's do 8. Why not? All right, ready? Stay ready.
Ready.
Can someone take charge of the camera? Make sure we're like in frame and focused and all that kind of stuff. Good. Hello robotics people and people watching at home. We begin. X equals t squared plus 3t plus 2. Silence. Good. And y equals 2t. What were the directions here? The directions were find dy dx and d squared y dx squared and find the slope and concavity if possible at the given value of the parameter. We're doing this at t equals 0. So goal, find dy dx, the slope of the tangent line at t equals 0, and find d squared y dx squared at t equals 0, which it is difficult to articulate exactly what that is. I guess you could call it the concavity. It's the rate of change with respect to x of the slope of the tangent line to the curve. We begin! From class we know, from class yesterday we know that dy dx is just dy dt over dx dt, and that, well, dy dt is just 2, and dx dt is 2t plus 3. So that was pretty simple, yeah? Well, the problem asks for dy dx at t equals 0, so I have this formula, and this formula tells me for a given t what the slope of the tangent line to the curve is at that t value. If I plug in 0, I get 2/3, and that's all there is to it. Good? Say good. Woo! Now comes the harder thing, which is this so-called d squared y dx squared. And this is the thing that we didn't quite finish in class the other day. So let's kind of slow it down a little bit for this moment now. What does this even mean? Answer, it means the derivative with respect to x of dy dx. And people find this quite hard, which is why I suggested in the video that you conceptually think of dy dx as something which depends on t. It is a function of t. In fact, it is 2 over 2t plus 3. So thinking of it as something that depends on t, you can, if it helps you, let z be dy dx. In other words, emotionally and conceptually assign a new variable called z to mean dy dx. Then that might make it a little bit more clear what's going on here. We're taking the derivative with respect to x of just z. I don't know if this helps or not. I think it does help some people. So that is basically dz dx. In other words, we're interested in the rate of change of z with respect to x. But now we see in a more transparent manner that z is a function of t, x is also a function of t. And so to compute dz dx, we have to do the same thing that we did originally, which is to compute dz dt and dx dt. This is a very long-winded, perhaps unnecessary, but perhaps necessary way of explaining that when one computes the derivative with respect to x of dy dx, what one must do is take the derivative with respect to t of dy dx over the derivative with respect to t of x. Does that help and explain things decently well? Okay, so if you watched the video, this is exactly what we did in the video. If you didn't watch the video, this is a sort of rushed version of that same conversation. Okay, so when it comes down to actually doing it now, what am I supposed to be doing? I'm supposed to be taking the derivative with respect to t of the thing I computed in part 1, which is, okay, I will think of this as 2 times 2t plus 3 to the negative 1, and the derivative of x with respect to t, I already have seen is just like 2t plus 3. Cool, cool? We're gonna like fill up a whole board with this problem, number 8. Anyway, so what is this derivative? It's like negative 2t plus 3 to the negative 2 back inside 2 over 2t plus 3. Am I still in frame? So this is negative 4 over 2t plus 3 cubed. And finally, I can plug in 0 and get that this is negative 4 over 27. Who's with me? Yo. Have I made a mistake or are we good? Someone back me up.
Because like if you put to the negative 1 power, then shouldn't you bring negative 1 down, not negative 2? Like the multipliers, like negative 1.
No, there was already a 2 there. So
Yeah,
I brought
I know,
down
but
a
you put the 2
negative.
at the end. So I assume that's another 2. No,
So the 2 is just chilling there.
Uh-huh.
Negative 1 comes down. 2t plus 3 to the negative 2. Back inside 2.
Oh wait, yeah, okay.
Good. Woo! Alright, let's do 3 more problems very quickly. 24 is, in a vacuum, quite a hard problem, but in reality, not hard, because it is basically the exact same thing we did yesterday in class, yeah? And the prompt is find the equations of the tangents at the point where the curve crosses itself. Where does this curve cross itself? Well, it's like not obvious, but it is obvious because we did this exact problem already. That if you look at x and you think of it as t times t squared minus 6, or perhaps even better, as t times t minus root 6, t plus root 6, and then we see that x is going to have the same value at t equals root 6 and t equals negative root 6. But so will y, because y is just t squared. And so when t is root 6, the coordinates of this point will be 0, 6. And when t is negative root 6, the coordinates of this point will also be 0, 6. And thus, this curve is crossing itself at the point 0, 6. Have we done that correctly? Yes, right?
Sure they absolutely use not absolutely all the points, because if you have like something that intersects that isn't on the x-axis or the y-axis, then
yes. What she's saying is your method worked for this particular problem because it was so easy, but if there was like a harder problem, it would be harder, and I agree with you, it would be harder. I don't know if there's like a general reliable method for doing this. But certainly here, the y value is symmetric with respect to t, and so like, okay. Good, anyway, we should still find the equations. How can we do that? Well, first we should, still doing number 24, find the equation for dy dx in general. It's dy dt over dx dt. And what is dy dt? It's 2t. What is dx dt? It's 3t squared minus 6. And so I can just now find dy dx at t equals root 6, and I can find dy dx at t equals negative root 6, and let's see, what do I get? Can I just like do this in my head? 6, 18, 12, so I think it's just root 6, yeah? No, 1 over root 6. Ugh. I am pretending to be smarter than I was. 6 times 3, 18, 12. So it's root 6 over 6. And this is probably just going to be negative root 6. Thus, The room is dark with the camera, right?
I don't know how
So
this works.
this becomes y minus 6 equals root 6 over 6x, and this line would be y minus 6 equals negative root 6 over 6x. Are those the two equation lines, the two equations of the tangent lines that you got? Good. 2 down, 1 to go. I've decided we're only doing one more problem, which is 34. Let's go. 34. By the way, what is 34? Does anyone know?
What do you mean, like the answer or the question?
Like, what's the shape? Yeah, good. In a perfect world, like your calculus knowledge like builds on a like deep foundation of pre-calculus knowledge. We did problems like this back in pre-calc C. What is it? Yeah, that's right. It's a parabola because x equals 4 cosine squared theta. So you can write that as 1 minus sine squared theta. Why would you want to do that? Because sine theta is just y over 2, and who's with me? And so that becomes 4 minus y squared. So actually, this whole thing, when you eliminate the parameter, which you were not asked to do for this problem, but you know, it's a problem. Specifically, it's the sideways parabola with thingy 4, vertex 4, opening left, and by the way, x is always positive, so this is like a truncated parabola. Is everyone now remembering doing a lot of problems like this back in like whatever, November? Woo! What are we actually supposed to do for this problem? We are supposed to find all points of a horizontal and vertical tangency. Well, I'm going to tell you right now that I don't expect any points of horizontal tangency because parabolas don't have points of horizontal tangency. Can I get the mild head nods? But I do expect a point of vertical tangency. Where do I expect that point to be happening? Right here. Good, let's see if the math backs that up. What should I do? I should compute the slope of the tangent line to the curve. It's dy dt over dx dt. Is the camera pointing in the right direction?
Yes,
Hopefully. I'm saying t here, but really it's like theta. The variable itself is irrelevant. What's dy d theta? It's just like 2 cosine theta. And what's dx d theta? Its chain rule says it's 8 cosine back inside. Negative sign. Thus giving me as my overall formula like something like -1 over 4 sine theta. So now I have a formula which will tell me for any given theta the slope of the tangent line to a curve, and just as I expected, there are no horizontal tangents because this thing is never 0. And there is a vertical tangent whenever the bottom is 0. That's when this expression becomes like infinite. So there will be a vertical tangent at theta equals 0 and pi. Theta equals 0 and theta equals pi. And if you plug 0 back in, here you get 4 comma 0, just as we sort of expected that there would be a vertical tangent here. And so, okay, in this case, we could use pre-calculus only, very pretty, to kind of learn everything we need to know. But if this were a more complicated curve, then the calculus would like tell us what we need to know about this. All right, how are you feeling about this topic?
Yeah.
Good. I'm going to collect this homework. Please tell me we have a half an hour of class left, do we?
Oh.
Just about.
Maybe so, we're gonna also collect the spring, so it's not homework.
Oh yeah, I need the spring break homework. That's right. So, please give me your spring break homework, which consisted of 4 sections. The 4 sections of homework were curve sketching problems, 4 of them. This is bookwork only. Second derivative test problems, 4 of them, very short. 2 optimization problems, and like a page or so of anti-differentiation problems. If you do not have this homework for some kind of reason, such as car accidents,
Thank you.
then it really doesn't. This is due like on Monday. So
No, I have
Tuesday.
break,
Good.
so.
Then I want all the spring break homework stapled, ideally in that order. Graphing second derivative, 2 optimization problems, and boom. And then I also want the little parametric thing that was due today. No, let's make it in 2 files. That would be good.
I'm like not sure.
Parametrics,
Or like.
spring break,
Wait, so are we just cutting out page 256?
spring break.
I know,
Not
but
sure.
page
Spring break.
I don't know what this is called.
Oh my God.
Wait,
This
he asked me
is
to
why.
all the bookwork from over.
Great.
Nothing is still on top of your
Started here. Let's see. First step. Just do that. Good. All right. Meanwhile, we're doing this lecture. We're just getting it done today, no matter what. We're just gonna skip around a little bit if necessary. All right. High quality video. Alright. I would like to introduce something this is going to take exactly 15 minutes, no more. And it is not really a new thing at all. Can someone raise that backward? What I want to talk about are linear approximations. What are linear approximations? They are just approximating a function using its tangent line. That's really it. So, if you give me a function, for example, and let's suppose that this function is for some reason kind of like annoying. But at a certain point, say, this one, a, I know exactly what the value of this function is there. And I also know exactly what the tangent line, what the slope of the tangent line is to the curve there. Well then, I can write an equation for the slope of the tangent line to the curve. The equation of the tangent line to a generic function f at a point A will be, it will be y minus f of A equals f prime of A x minus A. And what we may now do is think of this blue line as a function. And I will write it in a kind of standard function notation. I'm going to call it L. And, well, what is L? It's f of A plus f prime of A x minus A. Cool. And I shall refer to this as the linearization of f at x equals A. In other words, I have this function, and I can construct a new function, the new function being just the tangent line, and this new function serves as a decent approximation to my function f, as long as I stay near A. Now, if I go far away from A, then it's not going to be a very decent linearization of f at x equals. Let's immediately go to an example. Find the linearization of root x plus 3 at x equals 1. Go. can draw the line, the curve, root x plus 3. It's just root x. It's been moved 3 to the left. And where is this curve when x is 1? Well, it's at 2. I got something like that. Agree? Okay. Next question. What is the equation of the tangent line? 2. This function f at the point 1, 2. This is easily doable with some calculus. Are you done? Oh, great. So we can take the derivative. If we take the derivative, we get 1 over 2 root x plus 3. And then when we plug 1 in, we get 1/4. Yeah. Agreed? Woo. Therefore, we have this tangent line, and the slope of this tangent line is 1/4, and it goes through the point 1, 2. So the equation of this line is y minus 2 equals 1/4 x minus 1. And therefore, the linearization is, am I going too fast, or are we cool? The linearization is 2 plus 1/4 times x minus 2. Or, if you prefer, you can like combine like terms and stuff, and you can write this as x over 4 plus 7/4. Okay, so there's nothing really like deep going on here. You might be thinking, bless you, you might be thinking, Mr. Rose, aren't we just writing equations of tangent lines? We've been doing this for like a month. You are right. But the only new thing is how we are sort of conceiving of what we are doing. What we are now doing is sort of using this new function that we've defined, this linear function, as a kind of substitute for our real function. For example, suppose that you wanted an approximation of the square root of 3.98. Alright, now imagine you're in a world where you do not have a calculator, and you are some sort of engineer from the 17th century, and you need a really, really good approximation for the square root of 3.98 for some kind of reason, like you're building a bridge. How would you do this? Well, there are techniques that are available. No one in the world under 60 knows these techniques, but there is a like hand method similar to long division, which will enable you to take to compute digit by digit the square root of any number. But I don't know this. I learned it once, I forgot. You certainly do not. How are we going to do this, man? Linear approximation. She's a genius. Iris says, well, I don't know exactly what the square root of 3.98 is, but here's what I do know. It's probably, well, what's it pretty close to? 2. Good. That's a good first guess. Yeah, it is approximately 2. But I would like something a little bit better than 2. Can anyone see what is effectively, yeah?
0.98 over 4.
Yes, Lillian says, well, I have just constructed, a minute ago, I have just constructed the linearization to the function root x plus 3 at x equals 1. And can that be done more quietly? So I now conclude that the square root of 3.98 is approximately equal to L of 0.98. Who's with me? Right, because if you plug 0.98 into the f function, right, what I actually want is exactly f of 0.98. Maybe I should write it that way. The square root of 3.98 is exactly equal to f of 0.98. but that's what I don't know how to do. But what I do have is this linear function, which I constructed. And so this is approximately equal to L of 0.98. What is L of 0.98? Well, that's not hard at all because it's just a line. So I just compute L of 0.98. It's going to be, what is 0.98? It's like 49/50ths, yeah? So I'm going to plug 49/50ths over 4 plus 7/4. Is this the smart thing to do? Actually, I think it's better to plug it into the parentheses version, yeah, this version, right? So this is actually just 2 plus a 4th times 0.98 minus 1, which is negative negative 0.02, or maybe better write it as negative 1/50th. Who's with me? Okay, so then this is 2 minus 1 over 200. Careful. I think the actual answer is 399 over 200, yeah?
I'm sorry.
Or maybe, what's the better way to do this? It's like 1 and, yeah, maybe, yeah, it's like 1.998 is all it is, right? Is that right? Hold on. Half of 100th, which is 1.995. Thank you. Okay. I claim that the square root of 3.98 is approximately 1.995. Now, what's up? Did everyone follow what just happened here? I literally didn't do anything more complicated than just construct a tangent line to this curve and plug my point into the tangent line. Now, looking up, I am living in 2019. I do have a calculator. I don't know how my calculator does its magic, but let's just take the square root of 3.98 and see what the magic box says that the answer is. Whoa!
Yeah, you can.
Damn! 1.99499,373. Do you all see now that in like 2 minutes of some quick calculus and some small bit of a fraction arithmetic, I have gotten ridiculously close to the true value?
That's basically.
Yes. Now, I have cheated slightly by doing 2 things. One, I picked a number, 3.98, which was very, very close to 4. Does everyone appreciate that the farther away I move from the place where I anchored the linear approximation, the worse the approximation is going to get, because the tangent line in general will diverge, from the true function, right? I also happen to pick a function whose such that the slope of the tangent line is quite small, and so like the rate at which the tangent line diverges from this function is quite large. So if I tried this with like square root of 4.5, it wouldn't be quite as impressive, but it's still pretty good. Who's with me? Okay, good. So you may anchor your approximation in any given place. All right, good. And okay, that is one. So just maybe just very quickly then, what is the square root of 4.05? Approximately. It would be 1.05, which would be, according to this version, 2 plus 1/4 of 0.05. Which is 2 plus 1/80th. And now I don't know what to do now. That's like something. 161 over 80. Yeah, but how do I do that in decimal?
1/4 times
Maybe it would have been better to like
It's more
leave
like
it as
point-
0.05.
Yeah, 0.25.
Because it's really like 0.05 over 4. Well, I suddenly don't know what I'm doing. That's like it's like 2.0125. Is that right, Normie?
Yeah.
Woo! Yeah, because it's like a fourth of 5, which is like 0.25, and then you add in the right number of decimal places. If you grab the calculator and type in square root of 4.05 and tell me what happens. Again, confirmation via magic box says that the answer is quite close to 2.015. All right, good. Is everyone feeling the linear approximations? All right, what do we have time for? Okay. Well, good. I'll just continue with this lesson then. This is all pretty much great, and to be totally honest, this is all that's really going on, but there is a new approach. And the new approach is really not new, it is just the notation is new, and the new approach is to take very seriously these things called differentials. Alright, we have sort of already been taking differentials seriously sort of all year. What's a differential? It's like these little dy and dx things. Our book calls them differentials. Okay, so to sort of draw this picture again, we have some sort of function. And the big idea here, this is the sort of the idea. The idea is, let's suppose, this is my function f, let's suppose that it is somehow easy to compute f of a. So a is a particular value such that I can sort of quickly, easily, by hand, exactly however you want to say it, compute the value of f at that point. And that it is also, as we've just seen, easy to compute f prime of a. So I can differentiate this function and I know what the value of the derivative is at a. But it is difficult somehow to compute like f of x when x is not a. So it's hard to, this function's like hard to evaluate at other places. And so we choose to anchor our approximation at a. And well, what do? We construct the tangent line to the curve, and this is, and oh, I guess I should say that that is easy to do because I know the exact value.